space left for the discussions. Now, it's an honor and privilege to invite Dr. Arni Srinivasa to deliver the talk on cardiac rhythm dynamics and probabilistic modeling. Dr. Arni is a professor and director, a lab for theory and mathematical modeling, Medical College of Georgia, Augusta, U.S.A, and is currently serving as a member of AI-enabled technologies and system domains expert group, the CSIR, Government of India. He has developed various mathematical models for diseases like AIDS, bird flu, and swine flu, which have been used immensely in disease control programs in India and abroad, which in fact is an impact of all the work that Dr. Arni Srinivasa has been doing. Over to you, sir, for the talk. We look forward to it. Thank you.
Thank you. Thanks a lot, Dr. Sarita, and namaskar to all. And it is a great honor for me to speak on this occasion. And I want to thank organizer, Dr. Himanshu Chaturvedi, who is also in charge director. And just now, Dr. Raju Bal gave excellent inaugural address on the working of the importance of statistics. And I also want to congratulate all the staff, scientific staff of ICMR, NIMS, and the other distinguished speakers, Professor Diwan and Professor Mukhopadhyay. So it is a great honor for me, as I mentioned. I lived a long time in ISI Kolkata, and all my memories of, this professor's birthday. Professor is, Malanabis is generally known as a professor. There is no other professors. Usually he is only one professor, and doctor, rest of all known as doctors. So he is known as a professor. Today is the professor's birthday. So they used to give a lunch, very delicious lunch boxes, and we all used to enjoy that delicious lunch. And evening there is a Rabindra Sangeet. So I really recollect all those good memories. So with that introduction, today's my talk would be on the cardiac rhythm and the mathematical, stochastic modeling of that. And the purpose would be to give an overview of the thing, what is done with the the medicine background, and also the background to the, the bit of mathematics and the stochastic process, what is being done. So feel free to ask me questions at the end or during the talk. That is absolutely fine. And this is actually midnight for me in the US. So excuse me if my voice is a bit modulated or a bit strained. So let me share my screen. Can you all see the screen?
Yeah.
Okay. So this is the title of my talk: Cardiac Rhythm Dynamics and Probabilistic Modeling. The outline of the talk, if you see, I will first introduce basics on AI, artificial atrial fibrillation, that is also known as AFib. Then I will also discuss central research questions. What are the central research questions in AFib? And then I will touch on the data and probability models. And Dr. Chaturvedi already alerted me that this talk would be attended by non-statistics, non-mathematics background, also medicine, people from medicine also. So he asked me to take care the, it's a more overview, not deeper technical. So out of 20 slides, I have about at most two slides, only technical slides. So just to make sure that I want to inform that it will be mostly non-technical. Data and probability models, and then I will conclude the major outcomes of this particular research. So what is AFib, atrial fibrillation? AFib is mostly, it's kind of a most common heart or cardiac rhythm disorder. That means heartbeat is not properly done. The beat gets disordered, irregular beat, heartbeat. That's called atrial fibrillation. So AFib actually causes irregular heartbeat, as I mentioned. And there is a technical name for that. It's called arrhythmia. Arrhythmia, that means rhythm, arrhythm. Arrhythmia means, rhythm, non-rhythm, arrhythm. Arrhythm means it doesn't beats in rhythm or irregular heartbeat. So this is lungs. And we know that, heart is roughly located there. So irregular heartbeat need to be treated. So there are no recent estimates on the global burden on this particular problem, medical problem. But a study in 2014 by Chug and others, they say that worldwide about 30 million cases are there, could be there. Again, I take this as a pinch of salt. This is again a global, the group in Washington, global burden group, they study global morbidity, various things. So I don't take their study. They have been a lot of criticism on their study. They publish in Lancet many articles. It is funded by Bill Gates Foundation. So Gates Foundation, many people gave any projects funded by Gates Foundation, not taken many in the US very seriously, because there a lot of issues with the way the ethical issues, the data collection issues, and the sampling issues, and the data analysis. A lot of issues are there. So I take it as a pinch of salt, but they end up publishing in good journals. But the NIMS has a good scope to get this kind of problems as a national estimate for India. Take up this kind of studies to authenticate what could be this kind of AFib in India. So there is a good scope for NIMS to handle major issues which are actually important for India. And they have potential also. I have great respect for NIMS because they have they have very highly qualified statisticians and public health experts. So what AFib can be broadly classified into 4 categories. First one is paroxysmal AFib. It is actually occasional symptoms. Paroxysmal AFib is broadly within a week. The patient gets normal within a week. It could be from few minutes, patient having arrhythmia or irregular heartbeat, and come back to normal within a week. Persistent AFib is the patient suffers with arrhythmia more than a week, and medical intervention is needed to restore normal heart rhythm. Arrhythmia to rhythm. And then other kind of AFib is long-standing persistent AFib. This is clinically defined as more than 1 year the patient suffers with AFib. That means, the arrhythmia, irregular heartbeat, and medical intervention is needed to bring back the patient to normal heart rhythm. And then last one, permanent. That means the patient remains in arrhythmia. No treatment currently available to bring back the patient to normal heartbeat. So these are the 4 broader categories. And one can look at further literature from Keshav Kumar, brilliant article or review, and also Ferry in 2021. Sorry, and Vaibhav Singh in 2017. That article, further reading, I also summarize it based on the background, based on their research. One can look at for more further information. So broadly, this is what it is about AFib. So treatment. The treatment options are blood thinners. There are pharmacological treatments, are beta blockers. These are kind of also, they reduce the kind of a blood thinner. And then anti-arrhythmia medicines. The medicines to bring back heart rhythm to normal heart rhythm, bring back the irregular heart rhythm into normal heart rhythm. Tablets or pills are there. And there are other methods like cardiac surgeries and catheter ablation. So this is the catheter ablation part. That is what currently our study that I'm presenting is focused. So NIMS, like institutes like NIMS in India can take up a study to understand the burden of this kind of irregular arrhythmia. In my last talk recently, I gave at NCERT, where some of you also saw. That's what Dr. Chaturvedi mentioned. So these modern day cardiac problems were there, India, as I mentioned in other talk, until the 17th, 18th century, from the Mauryan dynasty to 18th century. A lot of epidemics occurred all over the world, including in India. But in India, there are no evidences of heart-related problems. But other parts of the world, there are evidences. But in India, the stress levels are almost not seen. The documented evidences they're showing. That's why some of the clinicians argue that perhaps that was the reason the heart-related research was not well developed in India, because there are no such problems. There are no stress levels. So diabetes and heart-related problems were not at all there until 17th century in India. That's what in another talk I presented regarding historical aspects and the economy, all that. Anyway, that coming to that, again, there is a big scope here to understand the catheter ablation, because this is very expensive treatment, expensive surgery. And impact of that is not very well known through modeling approaches. The data already there, but there are no mathematical or probabilistic modeling done. So given this is heart, roughly, this is like, give you overview of what's going on in the veins. And this part, the oval part, circular part, that's where the area of surgery, the surgeons perform area of a surgery. So they there's a catheter. That catheter they insert, and that try to like pacemaker, around the pacemaker, and then that try to through some signals, the heartbeat is controlled. They try to control for the 3 situations. Like out of 4 cases, the 4th one is permanent, but paroxysmal, persistent paroxysmal, long-term paroxysmal. So all 3 situations, catheter ablation is done in recent years to bring back the arrhythmia to rhythmic heartbeat. So this is the aspect where we collected the data and then done some modeling for that. So this is not an epidemic model, or this is not an infectious disease model. So most of the time I was at Kolkata, ISA Kolkata, Indian Institute of Science, most of the time building mathematical models, and also a bit of probabilistic models back there in Kolkata. But I also used to question, the importance of stochastic models there. But then for the last few years, like 5 to 8 years, we have been seeing that, stochastic models also practically been helpful in certain particular questions that I'm going to explain in today's talk. So recent research shows that catheter ablation is more effective for the sinus. So sinus rhythm, again, clinicians use. Sinus means normal. That's a clinical term. Sinus rhythm they use, the cardiologists use. That means normal rhythm. Then pharmacological medicines. This is the recent research conclusions. Sorry. For example, a researcher by January, he also done a clinical study to show that, this can be using catheter ablation. Surgeries can bring back to normal rhythm more likely than pharmacological medicines. Then Hakalati and also Nelson, they also done some studies. And then the Packer et al. There are many other people have done. So, these are for further references, the researchers and students who are there, they can look into this further information, how the research has been done, data collection, all these things. So the question it was asked is, what are the probabilities of returning to sinus rhythm? It is not about populations. It is not about getting a number of people infected. It is not about the burden of, disease. So we are not, that's the reason the question itself requires a probabilistic approach. The chances of returning to, given this treatment, given this catheter ablation surgery, given the surgery done on the patients, what are the chances of returning back? So that's why here mathematical traditional ODE, PDE, partial differential equation, which I have been applying, that won't fit here. So the team, this particular study is because of the initiation from the cardiologist, my former colleague, Dr. Adam Burman, is a cardiologist, and he saw, prior to this study, myself and another gynecologist, we both worked together on important projects for the infertility in the US. And we developed Markov chain models successfully and applied to the data, applied on the understanding, because what are the chances of getting a treatment, a woman with infertility can become a pregnant. In the US data, we would develop mathematical Markov chain models. And he saw that, and he wanted to initiate the study to understand because of his, and then this project launched in 2019, just before the pandemic. And then I also recruited Tejin Lee from Center for Bioinformatics. So we three formed a team. And then I got funding from Dr. Burman to take up this study. And then, after 4 years, they took time. We presented various places, but because of the pandemic, I became extremely busy due to the COVID. We could not get time to come back to although the work done in 2020, 2021, but we could not finish it up to publish. It published a few months ago in 2023 in the Bulletin of Math Biology, where the details can be seen. I'm going to explain you the central ideas and technicalities, but more details one can find. And these are the previous references. Mike Diamond, I mentioned about the infertility study in the US, which we initiated in 2013. So luckily, any mathematical modeling or probabilistic modeling to be done, it is good to have a collaborator who belongs to that particular domain. And we better learn that and then handle the problem. That actually improves. So they used to take me to the labs, clinical labs. I used to sit with the patients. So all these insights really helped understanding the modeling. So this is the one study we published in the deep learning models for Markov chain for the infertility problem in the US in 2020, and then prior to that 2017. So they're all available online. So that inspired Dr. Adam Burman to take up, he came up with a question that, Arni, can we come back with an answer to this particular problem, catheter ablation, which is not done in the US. So we want to take those policy level. Based on, we want to do more studies, not just once. Our study is not enough, whatever we have done. I'm going to explain you today. So other useful, this is about the clinical background. And then there are a lot of resources available on Markov chains and applications in medicine, particular medicine. For example, R.C. Yadav, a very well-known name from BHU, he wrote a brilliant article in 2022. Again, to the special issue of the Indian Institute of Science Journal, I edited it. And then his prior articles, 2018, 2019, very large articles, one can read a lot of applications and explain the basics of stochastic process. And I also like article by, all these listed articles, I personally really appreciate and I want to recommend to the students, Rajalakshmi and Ghosh. And then also Chariot, Wall, these people also, they worked on the Markov chain applications in medicine, Duffy, Chen, and Shrikant, Kumar, and these people have done in the, Shrikant, they have done in the ophthalmology, Markov chains in ophthalmology, Kumar and Yadava, again, 2019. Go, Bayati, they also done in the other research, other areas. And I gave a distinct GAN lecture series last year in Rohtak, MDU Rohtak. These lectures are also available. These are for the statistics and mostly statistics, PhD and postdoc and lecturers, all these GAN program. I gave 15 lectures that is available also. more technical stochastic process on the stochastic process available at GYAN website at IIT Kharagpur. Other resources. So come back to the research question, we have considered 5 populations. One is sinus, that is those individuals in the hospital who have no arrhythmia, and paroxysmal, persistent, long-standing persistent, and permanent. So 5 populations are considered in the hospital, and these are the populations which move from normal to paroxysmal, paroxysmal to persistent, or paroxysmal to normal, all various. The arrow with the direction indicates the individuals, the patients move from one category to other category. Except you see that here permanent, those who are reaching the permanent AFib, they remain there. There is no arrow going back from AFib. And then here for this, not for the senior scientists present there, just for the students, those are beginning students. So state versus variable. In this particular framework, usually there are 2 things are there in the modeling. One is stochastic approach or the deterministic or ODE-PDE approach. In the ODE-PDE approach, these are known as compartments, or they are known as variables. These are all population, because we are interested in the movement of populations. How these populations, each category changes, the dynamics of that. But in the stochastic framework, the same thing, they are known as states. And then we are interested in the understanding the movement. Here they call the technical term transition. Just there are technical terms, but conceptually the patients move. But how we look at the movement, whether we look at the questions related to probability or we look at the questions on the population dynamics, the modeling framework changes. So in this particular situation, these are considered as states. I will explain soon more detail. The states, because we will build a probabilistic framework with particularly we call Markov chain framework, where the patients move from one particular state to other particular state. And chances of moving, that's what we are interested. We are not interested in the population dynamics of each compartment. We are not interested here. We are interested in the chances of movement from one particular compartment to other particular compartment. So here, instead of compartment, that's it. Stochastic people, they use the word state. There is nothing wrong in using compartment. There is no patent for the compartment, only for the mathematical modelers. But it's a normal terminology to use that as a state. So some technicality. Let xt equal to 0. Here that means, here I mean it is a random variable describing this AFib status or a state, AFib health status of a patient at time 0. So this is state 0. I call the name state 0, state 1, state 2, state 3, state 4. There are 5 states are there, 0, 1, 2, 3, 4. And each patient can remain in the same state, need not always move to other state, could remain in the same state. Could remain in the same state. That's why I have this self loop for each state. That's why initially when we start a study in the hospital at time 0, initial state, x of t equal to 0, the patient could be at state here, state 0 or state 1, state 2, state 3, state 4. So the data is classified according to the patient at the initial state, initial time. Initially at t equal to 0, patient is located where? And after that, we study the patient transition or movement from one state to other state over the time. So the changes in the state, if there are any changes, each patient may not change. There is a self loop also there, as I mentioned. The self loops are there at each state. So the patient need not move, but if the patient moves, what are the chances of moving to other state? So we initially started record the day, record the information, and then observe the changes in the state. So x of t plus delta t we record, that means initial time and then small time or some time after, it could be small or large, greater than 0. We record the changes in the states. So this is again bit tutorial here. Again, this is continuous, time is continuous. So we monitor the changes of states continuously in the hospital. So time is continuous, but you see the states are well defined here. What is paroxysmal? You saw in previous slides. Paroxysmal from few hours to 1 week, persistent 1 week to 1 year, long standing more than 1 year. So they're all well defined. So clinically, they're all well defined. Hence, these states are disjoint or they are mutually exclusive. So that's why, these are discrete. These are all, the states are discrete in this particular framework. The time is continuous. And we're going to apply the Markov chain. I'm going to define that as well in the following slide. So this is a kind of a continuous time, discrete space Markov chain. The time is continuous and states are discrete. So 5 states are there: 0, 1, 2, 3, 4. So let's bit technicality here. This slide and next slide. Excuse me for that. So only 2 technical slides. So let there be n patients in the system, in the hospital system at time t equal to 0. So let us denote xm t plus delta t equal to I be the mth patient in the system out of n patients, capital N patients, mth patient, pick that patient. And then at time t plus delta t, the state of the patient, clinically health status, but stochastic terminology we call it state. Both are same, technically same. So don't worry about the terminology. So terminology, and just understand the framework. Framework is more important. Terminology, one can use whatever they want to, the students especially. So nothing to worry about the notation here. So again, I'll explain. This is a random variable with mth patient, t plus delta t time. This is a state. So in particular, this is a patient, time, state. Remember that. That's the random variable with 3 things. So it has this particular random variable has 3 things embedded in it. So total population, again, this distributed as based on the state of the patient. So capital N patients, all the patients are at particular each time point, t plus delta t, as we see that initially they are recorded, over the time also they recorded. So the total remains n. This is so the total population is constant, not dynamic, unless the patient dies. So the total states, the state space 0, 1, 2, 3, dies or patient leaves the treatment system, drops out of the treatment surgery or drops. So once the surgery done, patient is reported or not reported is a patient. Somewhere is there, maybe not coming back to the hospital to know whether, but then it is surgery done. So in this particular, we assume that they remain n, because of a short-term period. Of course, they are recorded, through mobile. Only during the pandemic, it is difficult, but more or less they can be recorded. Their status can be recorded. So we define the Markov property on the random variable. Again, you see that this is a patient, time. On the state space, S is a state space. So state space is set of all, state space consists of set of all states in the process on which the random variable jumps or picks any value over the time. So this is a state space. The random variable X picks up 0, 1, 2, 3, 4 in the beginning or after some time. Except for 4, once it is 4, it won't come back. So we define Markov property on x, m, comma, t on the state space as follows. So probability that xmt equal to j, it could be j is another state, ij, I mean j is also state, j could be one of these four. Given that x and k, for k between 0 to s, where s is less than t, s is less than t. So given that probability random variable picks the value j, given that it picks some value during this time interval, is equal to probability that xmt, the same xmt equal to j, given that xms, this record, note that here, xms, here xmk, that means prior to k, k could be between 0 and s, but that's equal to probability xmt equal to j, given that xms only, the last value, the last endpoint. That's how Markov property is a simple definition. Markov property on the random variable is defined. Then Pij stands for probability that the I to j, the transition occurred from a state I to state j, as you saw in the previous diagram. State is moved, state of the patient is moved. Pij t minus s. So equal to probability xmt equal to j, given xms equal to I. That means that at time s, patient m was at the state I. After s, at time t, the patient has moved to state j. That is ij, I to j. During the time t minus s, time units. So t is some date in a calendar, say August 15th, and today is June 30th. So it is about 46 days. So as this is about the state at June 30th, the patient was in state, say 1, I equal to 1. And the patient moved to 0, say recovered or cured to sinus in 45 days. So T minus S 45 days, probability that moving a patient from paroxysmal to normal in 45 days. What is that probability? As an example. So that's what Pij T minus S, the duration and the transition, both are included here in this notation. That's equal to probability xm T minus S equal to j and 0, because T minus S is starting from 0. These two are same in 45. So from June 30th to August 15th is same as just changing the the entire time scale. So it will be from 0th day to 45 days equal to June 30th to August 15th, same as 0 to 45. That's what it means. Probability of this is same. Probability of transition from June 30th to August 15th is same as probability of transition from January 1st to February 16th, something like that, February 15th. So something like that. So it is that these two probabilities are same. That's same as Markov property. So suppose now beta ij, this is important again, this notation. I mean, these are all these all terms go into the models. So beta ij indicates the rate of transition, that is move from state I to state j. And the betas usually here in the mathematical model, the transition rate, same beta here, but then there is a transition from one state to other state. The population movement and the average, statistical average is considered there. And then here it is beta ij rate of transition. So that is rate of, in terms of a COVID or other epidemics, we consider beta as a rate of transmission, not transition. So rate of transmission, these are technical terms, transmission in the virus transmission. That's why they use the transmission. That means virus entering into the body or entering into the body or into the cell of the body, if you are considering the cellular dynamics. So beta ij indicates the transition or the movement of a patient from I to j. Then the beta ij multiplied by the time unit delta t gives the probability of transition. So rate multiplied by the duration, we get the probability of transition from state I to state j during the time period. That is Pij delta t. You saw previous slide, t minus s. Now that replaced by delta t, the same, both are same. T minus s units, here delta t units, equal to probability xt plus delta t j xt. So t to t plus delta t, the duration is delta t, is a difference. That's what delta t is equal to beta ij delta t plus small o delta t, small delta t. So this is what the probabilities are derived from the data. I'll explain soon. And then the Kolmogorov forward differential equation, again, bit technical here. So we obtain the differential equation for the probabilities, the changes in the transition probability by dt. So I skipped several steps. So it is for now, you believe me, because I'm not explaining how to do this particular step. So this is all there in the article. These are all technicalities, one can look at, but summary, you understood already what is we are trying to do. So this particular equation, we solve that and then understand how the patients move and how long they stay in a particular state and the recovery due to the catheter ablation. So beta minus beta ij, pij, and sum of all the states, all possibilities, beta, you see that beta kj over k not equal to j. That means all possibilities from k to j, all possibilities, all the 5 states here, they move except state 4, where patient reaches permanent state. So that's it. So that's the end of the technicality. All the rest of we have proved 5 theorems of how the steady states occur, the properties, these theorems. One can look at the journal reference I provided, and I can send Dr. Chaturvedi if needed. That's available online, but Dr. Chaturvedi can share with you all. But I'm very open for any questions. And then I'll show you next is patient aggregations. How the patient aggregations we saw based on the models we developed and the data we have. So the data. So what we considered was, again, the Burman, my collaborator. So cardiologist, they have we took their data published in 2019 on the catheter ablation. So patient distribution at t equal to 0 is as follows. 0 number of sinus rhythm patients. Because sinus rhythm, we don't have to do catheter ablation. So that is 0. 300 paroxysmal, 139 persistent patients, 11 long-standing persistent, and no permanent. So there are no, so all 300 plus 139, 439 and 11, 450. Total 4, n equal to 450. So whatever the models we developed, we ran on them, this data. Of course, a lot of back and forth, because luckily, I have an access. So back and forth. So no model. Of course, a lot of data, a lot of theoretical work we do, but that just for academic purpose. But when we do practically, we need to validate everything according to the requirement of the be it a biologist or a medicine, a doctor or a physics, for whom we are applying the data, for whom we are applying the models, their satisfaction is more important. So a lot of back and forth, we did it, and then we come up with the first phase. The first phase of analysis consisted of first phase of analysis. You see that here. This is for the paroxysmal, the dynamics over the 60-month time period when we simulated. You see that there is an increase in the permanent number of patients due to in the permanent. They moved to permanent over the time period. But then luckily there is the aggregation is there. You see that in the aggregation is there in the paroxysmal, and also a bit of aggregation you can see here. Compilation of the patients, they more or less they are there. That's a good thing, paroxysmal. That means patient with the treatment, they are spending more time in the paroxysmal state. That means very short term, within a few hours to a week, they are having irregular heartbeat. That means they are safer. relatively safer. Of course, the zero sinus is more safer, but next to that, so that's a good thing from the data. And source, as I mentioned, Lee, Berman, and myself, we can see in 2023 the details. These and many other results are there. And the second phase of analysis, once the first phase, the first phase analysis indicates that, as I mentioned, patients may stay longer in paroxysmal, that's paroxysmal first state, than other non-permanent states. That's a fun observation. Remember that. And then also, you see, recollect that this is a particular framework we considered. You see that here, this is an absorbing state. Absorbing state is again technical term. The technical term absorbing means the patient reaches that particular state, patient remains there forever. That's an absorbing in the stochastic process that is defined. Defined as absorbing state. And the absorbing, when there are transitions are occurring among the 5 states, because of absorbing state, this is not irreducible. I put in italics. Irreducible. This is not. So roughly a stochastic process, a Markov chain, the states are irreducible. When they are closed, that means all possible transition could occur over the time infinitely within those states. It's called irreducible forever. But here you see that patient reaching here cannot come back. So this is not irreducible. That's one observation. So based on the 2 conclusions, one is that patients stay longer at paroxysmal state and is irreducible. So that helped us to understand that we took these 4 states, 5 states, and then we excluded state 4. And we call this particular 0, 1, 2, 3 as Q1. We divided the total matrix into 5 by 5 matrix into 4 by 4. 4 by 4, because patient reaching here, the probability to remain that is 1. Because patient in the permanent state remains forever there, the probability to remain there is 1. Only oscillation occurs among these states, or the transitions occur among the states. So we just took out the data of Q1, 0, 1, 2, 3, and we computed Q1 in the matrix. So 1 minus Q1 inverse or minus 1. So 1 over 1 minus Q1, that's what we constructed. So that value, those values, 1 minus Q, 1 minus 1, inverse of that, 1 minus Q1, inverse of that would be these values computed. Whatever the values you saw, that's, this is the computed values. This indicates, so 1 minus Q1, inverse of that gives us the average time. What is the meaning of the why did we compute that? Means when we take out the value there, the Q1, and then we build 1 minus Q1 to the power minus 1, that gives us the average time a patient spends. It's a typo here, it's a state, not stage. In a state before moving to another state. This is a state. So patient spending time in a state, average time spending in a state before moving to another state. So you see that 76.9 patient in the state 1 spend longest time in state 1 because of the treatment, that is surgery. And then next to that, you see that 72.8 and then patient in state 2 returning before the patient moving back to state 1 spent 69.7 months. These are months data. Yes, I just switch on the fan here. Yeah, so 76.9, 69.7, 72.8, and then you see all other values you can interpret like that. And 74 in the patient in the 0 to 1 before sinus before the treatment to some patients. But then, moving from sinus to arrhythmia, we are interested in the recovery of arrhythmia to normal rhythm. So the all values are there, but we are concerned 0 to 1, because that means sinus, a normal person became arrhythmia. That is also important, but this particular study that does not have any impact, any role with the correlate with the data of treatment surgery. So these are the main conclusion. As I mentioned, all other age-wise data all are there in that article. One can read the summary. This is because it's in a short talk. So key conclusions. So controlling AFib could be possible due to catheter ablation. Patient with the treatment could stay longer in the state of paroxysmal. Paroxysmal state is there, so good to treat at that stage so that the patient likely to come back to normal more higher. So continuous time Markov chains found to be useful in patient healthcare management here particularly. So the clinical gains are there, and also, as I mentioned, I was also curious back in ISI days. I tried to lay various stochastic models, but are not really tested on the published, but not really tested on the data. I also had questions, my teachers, all the seniors, the importance of stochastic versus math biology, promoting the math models those days, not much in the stochastic, but then, over the time, I see that, there are a lot of value also in answering certain questions using the stochastic framework. And further recent studies also, you can see that, for example, one of the study we are conducting, this is because of my Gyan lectures. I currently collaborating with Sujata Sukhia and Professor Kumar. She's a student, and Professor Kumar, professor at NDU. And general framework on continuous time Markov models. Again, just started recently last year after the Gyan lectures. And then the Manginis also, one should read this. I like this article, Manginis, on the reaction networks, and then how the reaction networks change because of continuous time framework. And Mehra et al., they also studied on the malaria control. There are many articles out there, which I come across. I'm listing you here. And also Burini, and they also like the cancer spread, cancer treatment. So NIMS also, cancer studies, all these, which are relevant to India. All the WHO or the UN agencies, they all try to pump on their research, their required research on the developing world. But then NIMS like institute need to stand strongly, thoroughly, because they have a talent. They have to stand thoroughly to do research which makes sense for population whose tax is paid, whose taxpayers' money is these government institutions running. So these kind of cancer research and a lot of research which makes sense, like a chikungunya. I was told that there are no attempts for chikungunya and dengue fever in India, although a lot of effect on the vaccination research done all over the world, because chikungunya, dengue are not there in the Western world, so they never focus on vaccines for these. But Kala Ajar, all this research, lot of research which makes sense for the populations there can be done, and they can do it also. And these are research, cancer spread, for example. And then also the last one, multi-level contours. So I applied on using complex plane bundles, using a climate research in 2021. That's also where I showed that, importance of continuous time Markov chains on the complex planes, about a 70-page article. And then there I explained how that can be applied for understanding the universal climate, local climate, but nothing to do with the medicine there. So these all some literature is there, and you saw the central idea. Thanks a lot for your attention. Questions are welcome. Sir, should I stop sharing the screen or keep it there?
Thank you, Professor Arni, for the excellent talk. In fact, we would like to have few questions.
Dr. Vishal has.
So
should I close the stop sharing screen, or should I share the screen?
Let the screen be there. If it is
Sure.
related to that, you may have to open it otherwise again.
Absolutely.
One question what I have, if you can, because I have seen the time what you have worked out at different states.
Mhm.
That was the outcome, as I understand that, especially the Q1 matrix when you call it. Okay. The Q matrix you call it, inside 0, 1, 2, 3 and this side also 0, 1, 2, 3. That is the important findings, what I understand. Yeah, it is Q1. But in the same matrix, the bottom you have written it is 0. Another side it is giving Q2, but bottom you are showing that this one is okay in the corner, but it is showing 0.
Correct.
I don't know why it is 0. But another thing is the transition which takes place from one state to another, that is the probability basically. We call it, is it not? So
Correct.
that transition beta which you have worked out, beta ij, somehow that I have missed it. How it has been done. So that is important for us to understand in which from one stage to another stage if it moves, then what is the chance? Because there could be reversal also. You said that from 0, 1 to 3, it can come back from 3 to 2 or 2 to 1 or 1 to 0. But if it is at the stage of 4, it cannot come back to stage of 3 or 2 or 1. That's what we understand. But what is the chance that it will be coming back? That is, reversal sort of probability is more important. If I have reached to the stage of 3, then whether I can come back to 2 or 1, what is the probability?
That's a very good question, Dr. Chaturvedi. Sorry, I could not see the. Let me. So, Dr. Chaturvedi, you asked the question. Yeah, now I can see. Yeah, this is a very good question. Excellent question. So, probabilities of all transitions we have done in the article. So, though, as you see that longer the period they stay there, that only I showed. Currently, I showed the 1 minus Q1 inverse of that. What you are asking also there, the probabilities they are all correlated with the duration of stay. So that let me share the screen again. So wherever the duration is higher, the probability to remain there is higher.
Okay.
That's so your point is very well taken. That's a good point.
From one stage to another stage also it is coming back.
Correct. Except 4.
Except 4, yeah.
Except 4, they are coming back. Yes. They're from long standing also treatment brought into the normal persistent. It is also yes.
To understand all this. Okay.
That's a good question. Yeah, all the from 0 to the some of the long standing also became normal. Some of them. Some of the persistent also became normal. Some of the long standing also became persistent. They came down. 3 to 2, 2 to 1 also seen in the data. So the longer they're staying there, lesser the transition. So longer the stage, that they are correlated. Your point is good, sir. Okay.
Vishal, if there is any question, you can just.
Yes, sir. Thank you. Thank you, Professor Rao, for your explanation. Sorry, it was echo. So thank you for your excellent talk and getting us to know about your excellent work where you have applied Markov chains. So there are a few questions in the chat box, and before that, Dr. Vishnu Rao, our former director, has also raised his hand. So he will ask a question first, and then we'll move on.
Please.
Dr. Vishnu, please.
Not good afternoon, good morning only, sorry. So thank you very much, Dr. Srinivasa Garu. You just spoke like a doctor. I am very appreciative of your talk. So I just wanted to, excuse me if I am for my ignorance. So one is that age is not being considered in the model. So how age varies with the model? Second thing is the treatment, suppose the treatment regime you are giving, in spite of that, they might move from 0 to 1, 1 to 2, 3 to 4, something like that. if at all they are moving, how the treatment is affecting the patient. Some patients it is better, some patients is not. So there is a aggregate effect treatment on the patients also. So how these two variables, age and the treatment effect, would change the model in specific. Thank you very much.
Thank you, Dr. Vishnuvardhan Rao. Garu, your question is very, very appropriate. Our next stage of analysis, you asked a very good question. Our next stage of analysis will be on the age. As I mentioned, because of pandemic, these all the other research questions got delayed all over the world. Not maybe same in the India, also in the U.S., everywhere. We could not focus, although we initially wanted to have the data on the age-wise also distribution. We could not have time to finish that study, large-scale study. Now we have a multi-center study based on the age we are considering. That's part one. So your point is well taken. And thanks also, you thought that I spoke like a doctor, I'm happy, I don't want to be, I'm happy as a mathematician, but I want to learn the other side of the science. So I presented that. And coming to the treatment impact of that, this is in the clinical trials, like a cancer chemotherapy. Chemotherapy is not, it is not a fully established treatment. It's not all the people will get success, or all the people will get success in particular age. Same like chemotherapy, radiation therapy, they're all under various clinical trials. That's why the patient's family need to undergo what sort of authorization. Treatment could fail. Similarly here, catheter ablation also not well studied, not many studies are done on the patient population. So that second part of your question also very relevant. And I hope that it's not nothing in my hand, that the researchers, the well-designed studies need to be done. I hope, it will be done everywhere in some time, but we have not done that, sir.
Thank you, sir. Thank you for your reply. And there are a few questions in the chat box, so I'll just read them.
Please,
One more hand
we have
is,
time.
So one question is, what is the advantage of using Markov to assess continuous rates of change compared to differential equations? And in the same person asks, can you be able to brief us about the sensitivity analysis performed to validate your Markov model? Yes.
Again, excellent question. The difference between the why I have done Markov models, that already in the slides I explained, the kind of a discuss between the states and the variable. So if you want, I can, should I go to the slides again? Or should I share?
Just explain, sir, that will be.
Thank you. So when we are studying the population dynamics, that means the change in each state of patient in the paroxysmal or different states of AFib, how each number in the compartment changes, numbers. So then we call these compartments and study the dynamics of these compartments by building a differential equation model. But the question here we are asking is the probability of transition or movement between the states, not the numbers. In terms of COVID, other things, or even for the cardiology, we are not here. That's also an important question, but that question we are not attempting here. That is the reason we have not built differential equations. Your question. Why it is continuous time? Time is continuous because we are not measuring the outcomes intermittently. We are measuring the outcome of the patient continuously since the surgery is done. Once the surgery is done in the hospital, at time t equal to 0, patient is monitored. Be the patient in the hospital, maybe in the home or somewhere traveling, the measurements are done and it's a continuous process. So the time is continuous. And then the previous state only matters, paroxysmal state, because they're all disjoint states. They're all mutually exclusive or disjoint, they overlap the definitions. That's why they're discrete. That's why continuous time, discrete. But your question is well taken. So these are all there in the GYAN lecture program where I gave 15 lectures on stochastic process, where I explained the different stochastic models and where we can use what type of models, how to build. And your sensitivity is a very good question. You know, that's a very important question. The betas. So yes, we have done the sensitivity analysis in the article. Sir, please see that there. That is there beta ij. How they are all sensitive because the sample size 450 is small. So we cannot interpret beyond hospital data. So hospital wise that is done. So sensitivity, we have to do it even for the differential equation model also, sensitivity to be done.
Thank you very much, sir. So there are two short questions and we'll stop after that. So one question is, I would like to know that how 1 minus Q inverse gives the average time of stay. I think that's what the person wants to mean. And the other question is whether we have taken comorbidities into consideration. Thank you, sir.
Good. That's a good point. The first question I did not understand. I want to read in the chat box. The voice was disturbed. But the second comorbidity point, that's a good point again. Yes, if the patient we found, that's actually, I should have explained that comorbidity part was done. Prior to that, whether they have any lung problems, whether the patient has any diabetic conditions before surgery. They performed under the normal situation, they performed the surgery. But transition could have a comorbidity, could impact the transition part. That is not done. That is nowhere done in the literature also. We searched. We have not done. The impact of transition, impact of comorbidity on the transition after surgery. That's a good point. That is not done by us or by any other group. That is not, it's a more cost-effective study. It is not done, but it's a good point.
Thank you. Thank you so much, sir.
But
and anybody? Sorry, sir. You were saying something? Okay, so anybody here in this room, if you have questions, please ask.
Thank you, sir, for the informative presentation. Just I have one query. This delta T is fixed for each value of S.
Yes.
So can we consider time varying transition probability rather than single time effect? This delta T for each value. This delta T is fixed for each value of S. S is one distribution. So can we consider time varying transition probability here?
Yes, yes. That's a good point again. We can consider time varying there. So here what we consider is a kind of a continuous time. It's called a jump in homogeneous process. So what you're saying also can be done. Here we are considered time is continuous and the states are discrete. And delta T could be more than 0, but it could be any time. We consider 60 months currently. You saw that aggregations. We have simulated for 60-month period. But it can be done. So that's a time varying only. What we did was time varying because time is changing all the time. It's continuously that changes all the time. So the patient numbers are changing all the time, but total population remains same. N is equal to 450 remain the same.
No, sir, my concern is that we are giving each value of S, this delta T is same for means equal weightage of time for each value of S. Rather than can we consider different value of T for different value of S?
Yes, yes, you are right. So different each patient when transition occurs, that patient's time is measured.
Rate of change.
Another patient changes another time. Another patient takes 8 weeks, 8 weeks considered. Another patient takes 7 weeks, 7 weeks. Another patient takes 14 weeks, 14 weeks. So each patient time and then the transition occurs. So all the such patients transition are taken and the rate of transition constructed based on the populations of transition. The numerator is number of transitions and denominator is total number of patients.
Yeah.
Good morning, Dr. Rao. I am Geeta Menon in NIMS. We have met earlier also in one of those H1N1 modeling which we did with PHFI. So it was an excellent presentation that you made. I am just trying to voice the opinion of others. One, that there may be many confounders, and in this model, age is a confounder. I'm not too sure that post-surgery comorbidity of the patient has no effect on the transition. You said there is no literature on it. One has to check that. I'm also thinking that what is the denominator? How many patients did you consider for this model? 450.
Yeah, thank you,
And
madam.
all patients monitored throughout, from the date of surgery till the outcome.
Yes. Yes, the comorbidity part, there is an impact of that. You are a good question, Dr. Meenan, madam. You are right. Comorbidity, I remember also H1N1, I was one of the NIV, National Institute of Virology. I was at ISA Kolkata. I remember all that time, it was great to work with you those days. The what is called, the comorbidity, yes. We also looked for the comorbidity is important. Like COVID also, we saw that those patients with diabetic and heart and lung issues, they have different levels of response. So comorbidity, they definitely doctors also believe, but the clinical trials, clinical studies are not done after the surgery because it takes a lot of expensive studies and they have to recruit the patients with the comorbid conditions, follow their cohorts. Recent 5 years, that's what due to the pandemic COVID, many things have disturbed this kind of clinical studies, but there is an impact. But what is that? The quantity we don't know. That's what I mentioned. The quantifiable values of comorbid conditions, what is that? But we are going to consider that point. Number two, what was the second question? The other
Number of patients we have already mentioned that was 450.
450. We did not change it. 450 was the total number of patients, and that did not change. We have only that data available because IRB approvals, all these things are needed, and the patient HIPAA agreements. Patient data need to be ethical. Also, we have collected that data that Burman et al. They have that data directly. We considered there. So there is no additional data. Then that data did not change. No deaths occurred.
Thank you. Thank you, Dr. Rao. The presentation has been excellent, and we have been receiving even the comments on the chat box that the presentation was really good. If there are any questions which are unanswered, the participants have shared their questions. We will share it across to you, and then we will seek your inputs on that. So thank you so much. And even this time that you have taken out, this is now morning. You started late night almost, and now it is morning. And the passion and the interest that you have is a demonstration, of your the skill set that you have. Thank you so much.